Space is vast, quiet place filled with wonders we are only starting to understand. Among its strangest creations are black holes, invisible giants that pull in everything, even light itself. Imagine a spot in the universe so powerful that nothing can escape its grip. That's a black hole. They have fascinated scientists for years, not just because they are mysterious, but because they challenge everything we think we know about how the universe works. In modern astrophysics, black holes are like puzzle pieces that don't quite fit, forcing us to rethink gravity, time, and even reality. Picture a star, massive and bright, burning for billions of years. When it runs out of fuel, it can't hold itself together anymore. It collapses, squeezing its enormous weight into a tiny point called a singularity. That's the heart of a black hole. Around it is a boundary, the event horizon, a kind of invisible line. Once anything crosses that line, whether it's a spaceship, a speck of dust, or a ray of light, it's gone for good. No one can see past it, which is why black hole feels like cosmic secrets. Scientists use them to test big ideas, like Einstein's theory of gravity, because they bend space and time in ways we can barely imagine. But here is the big question that keeps everyone awake at night. What actually happens inside a black hole? Once something falls past the event horizon, what's waiting on the other side? Does it get crushed into nothing? Does time stop? Or is there a whole another universe hiding in there? Nobody knows for sure. Some think the singularity is a place where all the rules of physics break down, like a glitch in the universe's code. Others wonder if black holes might be doorways to somewhere else, though that's more dream than fact right now. The truth is, we can't see inside. Our tools, telescopes, math, even our wildest guesses stop working at that point. But that doesn't mean we give up. Scientists keep studying the black holes, watching how they pull on nearby stars or spit out jets of energy. Every clue helps us get closer to understanding what's going on in there. It's like trying to solve a mystery with half the pages missing. For now, black holes remain one of the universe's greatest riddles, daring us to keep asking questions even if the answers feel impossibly far away. Once upon a time, in the vast darkness of space, a star was born. It started as a giant cloud of gas and dust swirling together until it got so heavy that it collapsed under its own weight. The center of this cloud grew hot and dense, and soon a bright new star began to shine. This was no ordinary star. It was massive, many times bigger than our sun. For millions of years, it burned brightly, turning hydrogen into helium in its core, like a cosmic furnace. But stars, like everything else, don't last forever. As the star aged, it started running out of fuel. The hydrogen in its core was used up, and it began burning heavier elements like helium, carbon, and oxygen. Each time it switched fuels, the star changed. It swelled up, becoming a red giant, its outer layers puffing into space. But deep inside, things were getting intense. The core was shrinking, squeezed tighter and tighter by gravity. For a massive star like this, the end was coming fast. When it finally ran out of elements to burn, the core couldn't hold itself up anymore. Gravity won the battle, and the core collapsed in a split second like a house of cards tumbling down. The collapse was so powerful that it triggered a supernova, a massive explosion that lit up the galaxy. The outer layers of the stars were blasted into space, scattering bits of stardust that might one day form new stars or planets. But the core? It kept shrinking, crushed by gravity into something so dense that nothing, not even light, could escape it. This was the birth of a black hole, a place where space and time get twisted in ways we can barely imagine. It's like a cosmic trapdoor, invisible but incredibly powerful, pulling in anything that gets too close. Not all black holes are the same though. The one we just saw came from a massive star, so it's called a stellar black hole. These are the most common kind with masses about 5 to 20 times that of our Sun. They are scattered across the universe, often found in pairs, orbiting each other after their parent stars explode. But there are other types of black holes, each with its own story. Intermediate black holes are bigger, with masses thousands of times that of our Sun. We are not sure exactly how they form, but some think that they come from smaller black holes merging together or from the collapse of a giant gas clouds in the early universe. Then there are supermassive black holes, the giants of the cosmos. These monsters have masses millions or even billions of times that of the Sun. They sit at the centers of galaxies, like the one in our Milky Way, quietly pulling in gas, dust, and stars. Scientists believe these black holes grew over billions of years, gobbling up material or merging with other black holes. They are like the anchors of galaxies, shaping how stars and planets move around them. Imagine a whirlpool in space with everything spiraling towards its center. There is one more type, a bit more mysterious, primordial black holes. These might have formed right after the Big Bang, when the universe was hot, chaotic soup. Tiny pockets of matter could have been squeezed so tightly that they turned into black holes, some as small as a grain of sand, others much bigger. We haven't found solid proof of these yet, but they could be hiding out there, drifting through space, or even affecting how the universe evolved. Every black hole, no matter its type, starts with a collapse, a moment when gravity takes over and reshapes the universe. From the fiery death of a star to the ancient echoes of the Big Bang, black holes are like scars in space, reminders of the incredible forces at work. They are not just endings though. The materials blasted out in supernovas can seed new stars, and the black holes themselves might hold clues to how galaxies form. In a way, they are part of a grand cosmic cycle where destruction leads to creation over and over again. Imagine you are standing at the edge of a cosmic cliff, staring into a black hole. It's not just a dark spot in space. It's a place where the rules of the universe bend and twist in ways that feel like magic, but it's all science. Let's take a walk through this strange world step by step and talk about what makes a black hole so wild. We will explore the event horizon, the singularity, the ergosphere, and a couple of other ideas that help us understand these mysterious objects, all through the lens of something called general relativity. First, picture a star that's run out of fuel. It collapses under its own weight, squeezing down smaller and smaller until it becomes a black hole. At its heart, it's the singularity. This is a point so tiny it's hard to even imagine. Smaller than a speck of dust, smaller than anything we can measure. But it's got all the star's mass packed into it, making it insanely dense. If you threw a piano into a singularity, it wouldn't just break, it would vanish into this point where space and time stop making sense. General relativity, which is Einstein's way of explaining how gravity works, tells us that the singularity is where all the normal rules of physics fall apart. We don't know exactly what's going on there because our math can't describe it yet. It's like the universe is hiding a secret it's not ready to share. Now let's step back from the singularity and talk about the event horizon. This is like an invisible line around the black hole, a boundary you don't want to cross. If you are outside it, you are okay. You can still escape the black hole's pull if you have got enough speed. But once you cross the event horizon, there is no turning back. It's not a wall or a fence. It's just the point where the black hole's gravity gets so strong that not even light can break free. That's why we can't see black holes directly. They trap everything, even the glow of stars. General relativity says this boundary is tied to the black hole's mass. The more massive the black hole, the bigger its event horizon. Scientists call the size of this boundary the Schwarzschild radius, named after a guy who figured out how to calculate it. Think of it like measuring the point where the black hole's grip becomes unbreakable. But what if the black hole is spinning? That's where things get even weirder and we meet the ergosphere. Imagine the black hole twirling like a top, dragging space itself around it like water swirling down a drain. The ergosphere is a region just outside the event horizon where this twisting happens. It's not a solid thing. It's more like a zone where the black hole spin makes space act funny. If you flew a spaceship into the ergosphere, you would get pulled along with the spin even if you didn't want to move. The cool part, you could still escape the ergosphere, unlike the event horizon. General relativity predicts this spinning effect, and it's why some black holes feel like cosmic whirlpools, tugging everything nearby into their dance. Let's zoom out a bit and think about what makes each black hole unique or not. There is this idea called the no-hair theorem, which sounds funny, but it's actually pretty simple. It says that black holes are like the plainest object in the universe. No matter what they were made from, a star, a planet, or a cloud of gas, they end up with just a few traits: mass, spin, and maybe an electric charge. That's it. No fancy colors, no weird shapes, no extra details. It's like every black hole gets a buzz cut, losing all its hair or unique features. General relativity helps us understand this because it describes how gravity smooths out all the messy stuff, leaving only the basics behind. So, what's the bigger picture? General relativity paints black holes as places where gravity rules everything. It's the force that crushes stars into singularities, draws the line of the event horizon, and spins space into ergosphere. It sets the Schwarzschild radius, strips black holes down to their bare essentials with no-hair theorem. Standing at the edge of a black hole, you would feel the weight of these ideas not just as math, but as a story about the universe's strangest corners. It's a place where time slows, space warps, and the impossible feels real. And yet, it's all part of the same world we live in, just waiting for us to understand it a little better. Now imagine a small spaceship, shiny and sleek, drifting through the vast emptiness of space. Its pilot, a curious explorer named Mia, has heard stories about black holes, those mysterious, invisible giants that swallow everything, even light. She has always wondered what would happen if we get too close. Today, her ship is nearing one, a massive black hole sitting quietly in the center of a starry swirl, pulling at everything around it like a whirlpool in the sky. As Mia's ship inches closer, something strange starts to happen. The black hole's pull, its gravity, is so strong that it tugs harder at the front of her ship than the back. It's like the ship is being stretched, pulled thin like a piece of dough being rolled out. Mia feels it too, her body stretching in a way that's hard to describe. Scientists call this spaghettification, a funny word for something not so funny. The closer she gets, the more the black hole's gravity stretches her and the ship, making them long and thin, like noodles in a cosmic soup. It's not painful yet, but it's weird, and Mia knows she is still far enough away to escape if she acts fast. But Mia is curious, so she drifts a little closer, her ship now caught in the black hole's grip. She notices something even stranger. Time itself starts to feel wrong. She glances at a clock on her dashboard, ticking away the seconds. Then she looks at a signal beaming from a faraway space station, where her friend Leo is watching her through a telescope. To Leo, Mia's clock seems to slow down, each tick taking longer and longer. This is time dilation, another wild trick of black holes. The closer Mia gets to the black hole, the slower times move for her compared to the rest of the universe. If she could see Leo's clock, it would be racing, hours passing for him while only minutes crawl by for her. It's like she is stuck in a slow motion movie while the world outside zooms ahead. Mia's ship is now dangerously close to a point called the event horizon, the point of no return. It's not a wall or a gate, just an invisible line in space. Once she crosses it, there is no going back. The black hole's pull would be so strong and nothing, not even light, could escape. Mia imagines what it would be like to cross that line. She would keep falling toward the center of the black hole, stretched thinner and thinner, her ship crumbling into tiny bits. Time would slow so much that to Leo watching from afar, it would look like she was frozen forever at the edge, never quite falling in. But for Mia, she would feel herself plunging deeper, everything happening in a flash. Mia's heart races as she thinks about that point of no return. She doesn't want to find out what's at the center of the black hole, not today. With a quick flick of her controls, she fires the ship's engines, pulling away just in time. As she speeds back towards the stars, she looks back at the black hole, a dark spot against the glowing sky. She thinks about how it bends space, stretches time, and traps anything that gets too close. It's scary, but it's also amazing, a reminder of how wild and strange the universe can be. Imagine a moment in the future where everything we know about the universe flips upside down. Scientists call it the singularity, a point where our understanding of physics breaks apart, like a puzzle with missing pieces. It's not just a wall we hit, It's a doorway to ideas so wild they sound like they belong in a sci-fi movie. Let's take a walk through some of these ideas like explorers stepping into a strange new world and see what might be waiting beyond. First, picture something called a white hole. If a black hole is a cosmic vacuum cleaner sucking up everything, even light, a white hole is the opposite. It's like a fountain in space, spitting out matter and light, never letting anything fall in. Nobody has seen one, but the math says they could exist. Imagine a star exploding not to destroy, but to create, pouring out new worlds. Some thinkers wonder if white holes could be connected to black holes, like two sides of cosmic coin. What if everything a black hole swallows gets spit out somewhere else as a white hole's gift to the universe? It's a crazy thought, but it makes you wonder what's on the other side. Now let's talk about wormholes, which are even stranger. Think of the universe as a big sheet of paper. If you want to get from one side to another, you could travel across it, but that takes forever. Or you could fold the paper and poke a hole through it, making a shortcut. That's a wormhole, a tunnel connecting two faraway places, maybe even different times or universe. Picture stepping through one, like walking through a magic door and popping out in a place where the stars look totally different. Scientists aren't sure if wormholes are real or stable enough to use, but the idea of bridges to other realities is enough to make your head spin. What if we could visit another universe, one with its own rules, its own story? Speaking of new universe, there is this idea about the baby universe. It's like the universe is a mom giving birth to little universes, each one a bubble with its own laws of physics. Imagine our universe as a giant tree and every branch is a new cosmos sprouting from it. Some say black holes could be the wombs for these baby universes, hiding the birth of whole new realities inside them. If that's true, every time a star collapses, it might just not die. It could be creating a brand new world. It's a beautiful thought that destruction could lead to creation, like a seed buried in the ground growing into a tree. Then there is holographic principle, which sounds like something from a dream. It says our universe might be like a 3D movie projected from a flat screen. Everything we see, stars, planets, even you and me, could be a hologram, a shadow of information stored on a giant cosmic surface. It's like we are living inside a video game, but the code is written on the edges of reality. This idea messes with your mind because it suggests the world we touch and feel isn't as solid as it seems. What if we are just patterns of light dancing on a universal stage? It's weird, but it makes you think about what real even means. Stepping beyond the singularity is like opening a book of possibilities, where every page is stranger than the last. White holes could be pouring out new matter, wormholes might lead to distant stars, baby universes could be blooming in secret, and the holographic principle might mean we are all a part of a cosmic illusion. These ideas aren't fact yet, just guesses, like lanterns lighting up in the dark. But they remind us that the universe is full of surprises, and even when we think we have hit a dead end, there is always another path to explore. But here is the weird part. What happens to all the stuff that fell in? Not just the physical bits, but the information about them. like what they were made of, how they move, or what color they were. This question puzzled scientists for years and became known as the information paradox. Let's picture it like this. So you had a favorite book and you tossed it into a black hole. The book is gone, right? But what about the story inside it? The words, the characters, the plot. Does all that vanishes too? Scientists used to think that once something fell into a black hole, everything about it was lost forever. The idea came from how black holes work. They have this invisible line called the event horizon, like a point of no return. Once you cross it, you are gone, and no one outside can see what happens to you. The black hole just sits there looking the same no matter what it swallows. It's like a cosmic shredder that leaves no trace. But then, a scientist named Stephen Hawking shook things up. He figured out that black holes aren't totally quiet. They actually leak a little bit of energy, kind of like a faint hum. This energy, called Hawking radiation, comes out slowly over billions of years until the black hole shrinks and disappears. Here is the catch. This radiation doesn't seem to carry any details about the stuff that fell into the black hole. So if the book you threw in had a love story or a mystery, none of that would show up in the radiation. It's just random noise. This was a big problem because science says information like the details of your book should never disappear. It's supposed to stick around somewhere, somehow. That clash between what science expects and what black holes seem to do is the heart of the paradox. This paradox bugged everyone. If information really got lost, it would break some of the rules that make our universe tick, like the laws of quantum mechanics. Those rules are super strict about keeping track of everything. Losing information would be like saying part of the universe could just forget what it was. On the other hand, if the information wasn't lost, how was it getting out? Scientists scratched their heads and came up with some wild ideas to solve this mystery. One idea was something called a firewall. Picture the event horizon of a black hole not as a quiet boundary but as a blazing wall of energy. Anything that crossed it, like a book, would hit this firewall and burn up instantly. The information wouldn't get lost, it would be scrambled and blasted out as a part of the radiation. But this idea has a downside. It suggests that falling into a black hole wasn't smooth, like scientists thought. Instead, it would be like hitting a cosmic brick wall, which didn't quite add up with other things we know about the black holes. Then came another idea called soft air. This one's a bit gentler. Scientists suggested that black holes might have a kind of invisible fuzz around them, not actually hair, but tiny bits of information clinging into the edge. When stuff falls in, some of its details get stuck in this fuzz. Over time, as the black hole leaks radiation, those details could slip out, carried away like dandelion seeds in the wind. It's a clever way to save the information without breaking the rules. But it's tricky to prove because this hair is so faint we can't even see it. Another idea floating around is quantum remnants. This one says when a black hole shrinks down to almost nothing, it doesn't vanish completely. Instead, it leaves behind a tiny speck smaller than a grain of sand, packed with all the information it ever swallowed. So, your book story would still be there, squeezed into this small remnant. The problem? These remnants would be so tiny and weird that finding them or understanding them is a huge challenge. So, where does that leave us? The information paradox is like a cosmic detective story with no clear ending yet. Scientists keep digging, testing new ideas, and building better tools to understand black holes. Each theory, firewalls, soft hair, quantum remnants offers a piece of the puzzle, but none have solved it completely. It's a reminder of how strange and wonderful the universe is, always keeping secrets just out of reach, waiting for someone to crack the code. Imagine staring up at the night sky where stars twinkle like tiny lanterns. Among them, hidden in the vast darkness, are black holes, mysterious objects that bend the rule of the universe. These aren't just strange phenomena, they are like teachers, whispering secrets about reality itself. A black hole forms when a massive star runs out of fuel and collapses under its own weight, squeezing into a point so dense that not even light can escape. This makes them invisible, but their pull is so strong they twist everything around them, including the very fabric of space and time. By studying black holes, we start to see the universe not as a simple place, but with planets, stars, but as a wild, flexible puzzle that challenges what we think we know. Picture time as a river, flowing steadily from past to future. Near a black hole, that river goes haywire. If you got close to one, time would slow down for you compared to someone far away. This isn't science fiction, it's what Einstein figured out with his ideas about gravity. Black holes warp space-time, the invisible stage where everything in the universe happens. Space-time isn't just a backdrop, it's a stretchy like a rubber sheet. A black hole is like a heavy ball dropped onto that sheet, bending it so deeply that things like time and cause and effect get scrambled. If you tossed a ball toward a black hole, it might seem to freeze at the edge, never quite falling in, even though it's long gone from your perspective. This weirdness makes us question, is time always steady, or is it just a story our mind tells us to make sense of the world? Now let's think about causality. The idea one thing leads to another, like flipping a switch to turn on a light. Black holes mess with this too. At their edge, called the event horizon, the rules break down. If you cross that line, you would be pulled into a place where the future becomes certain. You are heading to the center, no way out. But for someone watching from very far, you would seem stuck forever at the horizon. This makes us wonder if cause and effect are as reliable as we think, or if the universe plays by rules we haven't fully grasped. Black holes act like a cosmic mirror, reflecting back questions whether reality is fixed or if it depends on where you are standing. Could black holes also hold clues about the universe began? Some scientists think so. Way back at the Big Bang, everything, space, time, and matter was squeezed into a tiny point, kind of like the heart of a black hole, but in reverse. Black holes might be like little echoes of that moment, holding secrets about the conditions that sparked the cosmos. There is even a wild idea that the stuff falling into a black hole doesn't just vanish but might connect to another universe like a bridge to somewhere else. We don't know if that's true, but it's exciting to think that black holes could be doorways to understanding the birth of everything. In the end, black holes aren't just scary voids in space, they are like puzzles that makes us rethink reality. They show us that time can bend, causality can wobble, and the universe might have started in a way that's still written in the depths. They remind us that world isn't always what it seems. It's deeper, stranger, and full of mysteries waiting for us to explore. So next time you look at the stars, think about those invisible giants out there. quietly teaching us that reality is far more magical than we ever imagined. Now let's pull back and think about what we have learned. A black hole starts with a star's collapse, forming a singularity wrapped in an event horizon. Anything that crosses that line gets stretched, pulled, and lost to the outside world. Inside, space and time go haywire, and everything might get crushed or transformed in ways we can't fully grasp. That's the heart of the story, a place where gravity rules and mysteries thrive. But here is the thing, we don't have all the answers. Scientists are still puzzled by what really happens at the singularity, or if black holes hold secrets we haven't dreamed of yet. They study, they argue, they build giant telescopes, but some parts of the puzzle are still missing. And that's okay. It's what makes black holes so exciting. They remind us how much there is to discover. So as you look up at the night sky, think about those invisible giants out there, swallowing light and bending reality. What's really going on inside a black hole? Could it be a key to understanding the universe, or a question we will chase forever?